All right, in this video, we're going to look at titration calculations. Previously, we've looked at the concept of a titration being a laboratory method of combining an acid and a base in hopes of determining the concentration of an unknown acid or base solution. When we titrate in the lab, we get data that would look very similar to this. And in fact, we're going to do a lab that is almost identical to this set of calculations and data. We are going to titrate hydrochloric acid and sodium hydroxide. The first thing we need in any kind of a titration calculation is a balanced equation. It's just like a double replacement, so we have to write the formulas for hydrochloric acid and sodium hydroxide. I got my HCl and my sodium hydroxide. This is an easy equation because everything is either +1 or -1. Sodium's +1, hydroxide is -1. If I do a double replacement, I can either switch the positives or the negatives. I usually just switch the positives because they come first and there's really no other better reason. So I'll have sodium with chloride and then hydrogen with hydroxide. And again, everything should be nice, easy ratios, +1, -1. Now we also kind of mentioned that HOH is also known as water. So I don't care if you write it as the HOH, or if you would prefer, you can write it as water. If needed, we would have to balance with coefficients, but this one is balanced with all 1-to-1 ratios. All right, so now the general setup of my titration. I would have a burette, my long skinny burette with the stopcock on the bottom, and then I'd have a flask underneath. Hey, that's pretty good. I am not mad about that. All right, so the solution of known concentration will always go in the burette. There has to be one of the two original solutions that you know the molarity of. In this case, it says 20 milliliters of 0.5 molar sodium hydroxide are needed to neutralize 40 milliliters of the hydrochloric acid. So the known molarity is the sodium hydroxide, and that must be in the burette. So the sodium hydroxide is in the burette. The unknown concentration is the solution in the flask. So that would be the HCl. And even though they don't mention it, there would be some kind of acid-base indicator. Now, it doesn't have to be the base in the burette. That'd be convenient because they both start with B. It's just the solution of unknown molarity. Known molarity, hello. Known molarity, that always goes in the burette. And the unknown concentration always goes down in the flask. All right, so we mix these solutions. I've got 40 milliliters of hydrochloric acid. So down in this flask, it would be 40 milliliters of acid. And then I'm going to drip, drip, drip in the base until I hit the equivalence point, which that would have been met at 20 milliliters of sodium hydroxide. So I would have added 20 milliliters added. Or sometimes a lab might say, what was the volume of, in this case, sodium hydroxide delivered? So we needed to deliver 20 milliliters of the sodium hydroxide to neutralize 40 milliliters of hydrochloric acid. Neutralize just means to completely react. We react the two solutions until we hit that equivalence point, the magic point where we have equal moles of acid and base according to the ratio in the balanced equation. So in this particular equation, it would be a 1-to-1 ratio. All right, so now this is basically just some solution stoichiometry. We always start with the solution of known concentration, and I want to solve it for moles. Since I know that it was a 0.5 molar sodium hydroxide solution, and I know that molarity is moles per liter, I can solve for moles as long as I know the volume used. We used 20 milliliters, which is really 0.02 liters. We'll cross multiply to solve it for moles, and we'd be looking at about 0.01 moles of sodium hydroxide added, delivered, used. All we did was take that sodium hydroxide solution and turn it into moles. And we knew that it was originally 0.5 molar. Well, now again, the idea of the equivalence point is that you are at the ratio in the balanced equation. The ratio in the balanced equation is a ratio of moles. So I stop the titration in this particular reaction with a 1-to-1 mole ratio of acid to base, which makes step 3 super easy. Now, if you want, you can be fancy with it, and you could say change moles of known solution to moles of unknown solution. And you could say, well, I knew that it was 0.01 moles of sodium hydroxide. We're trying to figure out how much acid was present. And so if I know I'm at the stoichiometric ratio, I can cancel moles of the known concentration and switch it to moles of the unknown, which in this case is super easy because it's a 1-to-1 ratio. So if it's a 1-to-1 ratio, you might not even write this step on paper. It's just the same. 0.01 moles, but now it's HCl. We stop the titration at the equivalence point when the moles of acid and base equal the ratio from the balanced equation. Again, if you don't need to show this step, I'm cool with that. Because usually the ratio in the balanced equation for these neutralizations isn't super crazy. 1-to-1, 1-to-2, 1-to-3, something along those lines. Hey, now we can do the concentration of the unknown. The unknown solution in this case was the hydrochloric acid, molarity of the HCl. Molarity is moles, which now I know, 0.01 per liter. And we had to know the volume, so they told us that originally there was 40 milliliters, which does have to be converted to liters, 0.04 liters. I know the moles, I know the volume, I know the molarity, 0.25. That's the concentration of the HCl. It is really solution stoichiometry. As long as we know the volume and the molarity of one solution needed to reach the equivalence point, we can solve this one for moles, use the ratio in the balanced equation to get moles of the unknown solution, and then as long as we knew the volume, we could calculate molarity, moles per liter. This is nearly identical to one of the labs that we'll do. Now, the other thing that I kind of like about this one is that it does make sense. So the acid ended up being 0.25 molar, and there was 40 milliliters. The base was twice as concentrated. The base was 0.5 molar. Look at this. You needed half the volume. So half the volume, but double the concentration, ended up being the same moles as the HCl solution. It was double the volume, but half the concentration. But those two solutions had the same amount of moles. It was a 1-to-1 ratio in the balanced equation. Brilliant, right? Yeah, these are great. Okay, so that's a pretty straightforward one. I like that one. And we're going to use these solutions in the lab quite a bit. Let's pick out a couple other options. Okay, so in number 2, 35.5 milliliters of 0.345 molar sulfuric acid are used to titrate 42.7 milliliters of potassium hydroxide. What is the concentration of the potassium hydroxide? All right, I can do this. Again, the setup. So I'd have a burette, a long skinny burette with a little valve stopcock on the bottom and a flask. That one's kind of lopsided, but I can live with it. The solution of known concentration goes in my burette. This time the molarity that we know is 0.345 molar sulfuric acid, H2SO4. That will be delivered to the potassium hydroxide. The burette has my acid this time. And the flask starts with the base, potassium hydroxide, along with an indicator. The indicator should turn colors, indicating when I've hit the stoichiometric ratio in the balanced equation, the equivalence point. Sulfuric is a strong acid and potassium hydroxide is a strong base. So when I stop this titration at the equivalence point, I want an indicator that would turn colors around a pH of 7. The solution should be neutral. All right, so we had 42.7 milliliters of this potassium hydroxide, 42.7 milliliters. And then we added the sulfuric acid, drop, drop, drop. And it ended up that we needed 35.5 milliliters. All right, so step 1, we need a balanced equation. This is the reaction of H2SO4 sulfuric acid plus potassium hydroxide. Now there are a couple polyatomics that you'll run into. I mean, hydroxide is by far the most common when we do acid-base chemistry. But they give me the formula for the sulfuric acid. It's like hydrogen sulfate, where hydrogen is, that's a +1. Sulfate is -2. That's why there's the 2 hydrogen ions. +1 on the potassium, -1 on the hydroxide. All right, so it's like a double replacement. I'm going to switch the potassium and the hydrogen. So I'll have potassium with sulfate and hydrogen with hydroxide. And we did say that one of the products in any neutralization should always be water. So that's my HOH, also known as water. I got to check all my charges. Potassium was +1, but sulfate is -2. So I'm going to need 2 potassium to make that neutral. Water's cool. +1, -1. This one does need to be balanced. Oh, brother. 2 hydrogen. We'll need 2 hydrogen. Here's like the hydrogen. Then there's 1 sulfate, 1 sulfate. 1 potassium, 2 potassium. I need 2. That also now gives me 2 hydroxide. But again, by putting the 2 out in front of water, I get the 2 + 1 hydrogen ions, and then the 2 - 1 hydroxide ions. And she's balanced. but it's not a 1-to-1 ratio. Well, in this case, the sulfuric acid has 2 hydrogen ions. So if I'm going to completely neutralize, completely react the sulfuric acid, I need 2 hydroxide. Well, since potassium hydroxide only has 1 hydroxide ion, we need that 2 out in front, that coefficient 2. So when this solution is neutralized, when we're at the equivalence point, I'm actually going to have double the moles of potassium hydroxide. Sweet. All right, so step 2. Step 2 is to start with a solution of known molarity. I know that the acid is 0.345 molar, and that is H2SO4. And molarity equals moles per liter. We want to solve for moles. Again, this is like solution stoichiometry. I want to be able to use the ratio from the balanced equation, but it's a ratio of moles. So as long as I know the molarity and the volume, I just have to switch it to liters. So this will become 0.0355 liters. I can solve it for moles. We cross multiply, and I get about 0.0122 moles of acid, H2SO4. Awesome. At this point, we're ready to do stoichiometry. I want to know the concentration of the potassium hydroxide. Concentration is moles per liter. Well, I know the volume of the KOH. I'll just have to switch it to liters, but I need to solve for the moles. Step 3 is kind of optional. I'll even write that. Optional. I want to now convert moles of acid to moles of base. Sometimes it's obvious, and you don't need to write it on paper. For example, there's twice as much base. There's twice as many moles of KOH. So what I'm going to end up doing is taking my moles of acid, H2SO4, and I'm going to multiply by 2. If it's not obvious to you, then you just write it out. So my moles, 0.0122. Here's the known solution, H2SO4. We'll set it up. We'll cancel moles of the known. The original was the acid. Whoa, that's not an M. Moles of H2SO4. I want to switch it over to the unknown, the KOH. And yeah, it's a 2-to-1 ratio. I can cancel moles of sulfuric acid. And now this is pretty manageable, right? 0.0244 moles of KOH. When I have this 1-to-2 ratio, it should be a neutral solution. I need twice as much KOH, so I get the same amount of hydroxide to match up with my hydrogen. That's when the solution is officially neutral, when hydrogen equals hydroxide. All we form then is water and some kind of an ionic salt, which potassium and sulfate are neither acid nor base. I'm ready for step 4 then. The molarity of the unknown, in this case, base. Moles per liter, 0.0244 moles, divided by the volume in liters. So it took 42.7 milliliters. We'll just switch that over to liters. 0.427. We plug it in our calculator and we're done. Oh, brother. How about, I'll go 3. 0.571. And then that should be the KOH. Oopsies. Potassium hydroxide. There. KOH. Every titration calculation will follow the same pattern of steps. We need the balanced equation. Then we start with the solution of known molarity and volume. We solve it for moles. We consult the ratio in the balanced equation. So even if you don't want to write this, I can live with that. But you at least need to consult the ratio in the balanced equation so that you can get from moles of known solution to moles of unknown. I'm okay if you don't show that third step. But then in the end, I would show the molarity of the unknown is moles per liter. Nice, huh? Predictable. They're all set up the same way. All right, for kicks, last one. Last problem of the entire year. It's actually kind of crazy, huh? All right, we better enjoy these last couple minutes while they last then. Okay, here we go. We have a 20 milliliter sample of hydrochloric acid titrated with 27.4 milliliters of 0.0154 molar barium hydroxide. What is the concentration of the hydrochloric acid? Step 1, balanced equation. This is hydrochloric acid, which is HCl. And you don't have to write the charges in, but sometimes I like to remind myself, +1, -1. Barium hydroxide. Barium hydroxide. If I look on the periodic table, barium's in the second group. +2 hydroxide -1. That means I need 2 hydroxide to make this neutral. All right, so we switch the positives or the negatives. That means I'll have barium with chlorine +2 -1. I need 2 chlorines. And then the other product is a slam dunk. Hydrogen hydroxide, which is neutral. +1 -1, also known as water. And I really don't care if you just write water. I'm fine with that. This one is not balanced, so I need to fix it a little bit. I'm going to end up needing 2 hydroxide, which here's that -1 hydroxide, -1 hydroxide. 2, I got to go all the way out in front. 2 hydrogen. Here's the +1 hydrogen. Now I need 2. +1 hydrogen, I need 2. That also gives me 2 chlorine, but what do you know, I wanted 2 anyways. Simple. All right. Step 2. There's always one solution that you'll know the molarity and volume. It happens to be, in this case, the barium hydroxide. It's 0.0154 molar barium hydroxide. Molarity is moles per liter. And I know the volume. 0.0274 liters. We do have to switch that volume to liters. We cross multiply. And let's see here. Maybe like tiny. 0.000422. That's moles of barium hydroxide. Done. Awesome. Now, again, at this point, you might be able to skip step 3. I eventually now want to be able to use the ratio in the balanced equation to go from the known solution to the unknown. What? Again, these aren't going to be super wacky ratios. So maybe you can look at that and say, oh yeah, it's a 1-to-2 ratio. Maybe you're good enough that you can skip to step 4, which would be calculating the molarity of the unknown hydrochloric acid. And maybe you can say, well, it's a 1-to-2 ratio. So if this is moles of my base, my barium hydroxide, I'm just going to double that to get moles of acid, which would then be 0.000844. And I could live with that. And then we have to know the volume of the unknown. So this was 20 milliliters, or 0.020 liters. And we plug it in. And we'd be looking at about, oh brother, 0.0422 HCl. Maybe that's where you're at. It's an easy ratio. You have to consult the ratio in the balanced equation. I'll put that down. Step 3. We must consult the ratio in the balanced equation. Even if you don't write anything down, you still have to look at it. And again, if you're unsure if the ratio is something wacky, well, then you set it up like a little stoichiometry, a little mole stoichiometry. Take moles of the known and set up the proportion with the ratio from the balanced equation. But again, they're usually not crazy. So if you can consult that ratio in your noggin, I'm okay with that. Take care of moles of the unknown and divide by the volume of the unknown then. Bingo, you got it. And that is the last concept of the entire course. Calculating the concentration of an unknown acid or base using this method called a titration, in which we're combining the acid and the base until we hit the equivalence point, which just means that we have hit the ratio from the balanced equation. The way we know we hit the equivalence point is by using an appropriate indicator that turns colors at the appropriate pH. So now that you are masters of titration calculations, right, it'll be time to hop in the lab and try a few.